Good morning, welcome. I'm Steve Crockett with Colmorgan L2 Systems Engineering based in Radford, Virginia. This is the S700 series Session 1 WebEx. We're going to cover the S700 installation, the wiring, the mounting. We're going to go over grounding, noise checklist, connector specifications, motor power and feedback connection, the three-phase wiring into the amplifier, regen connections, and DC bus sharing. Okay, the best locations for getting information off the web for the S700 product. We've got two locations that we pull the most information from. The first being the site from Europe. It is www.servostar.de. We refer to it as the wiki site. Take a quick jump to it. Okay, from the wiki site here, you can see you have it's in German and British English here. It covers all the products that are supported out of the Colmorgan German office. Simply, you can go down the page, of course, for servo amplifiers. I'll lead you straight to the S700. And for the S700, this is the most recent and closest information to the engineering group that developed the product. So I'd recommend this one for the most detailed information. It's very simple to navigate from the table of content, literature, software, hardware manuals. And I'm going to be working from the hardware manual some today, so we'll open it up real quick, give you a look at that. So here is the high current S700. For this first section, the attention and focus is going to be on the high current unit. Of course, there's similar manuals on the website here for the low current version hardware, but we're going to be talking and making reference to the S748 and the S772, which are the high current and have their own. It has its own manual. Okay. All right. We have a second website that we go to for information, North American website, and it takes into consideration the product that's shipped out of Radford, Virginia, Colmorgan, Radford, Virginia. And it has similar information. Sometimes it's just not as much information found on the North American website as it is in the wiki site from Germany. But as you can see here, we have similar information, the features, specifications. We've got the manuals for the products, literature, including the catalog, sales brochures, and whatnot. We have software and firmware for updating in the drives. And of course, we have application notes. Okay, so North American website has information as well. Okay. The S700 product was, it's the 4th generation product. The original drives for the S700 were, or in front of the S700 was the 600, the S600, the S400, the S300, and now the S700. They were all designed in Dusseldorf, Germany by the engineering group which was known as Zeidel, and Cole Morgan acquired Zytel sometime back in the late 90s, and then now it's introduced only as Cole Morgan, and it's the drives for North America. As of December 2010, the S700 is sold in the U.S. The S700, where it's made, it's manufactured in Austria, the Zytel manufacturing facility. We stock and repair the product out of Radford, Virginia, and we support it out of Radford, Virginia. I'm one of approximately 7 L2 systems engineers that support the product. We sell through the distribution channels as well as out of the customer support group here in Radford. And we have local field sales engineers and technical sales specialists located in North America for the product. Part number schemes. The S700 has many different current ratings, as we can see here. The continuous current rating of the amplifier is on the low currents. We have an 01, an S701. It's 1.5 amp continuous. An 03, an 06, and a S712 and a 724. That is what we would refer to as the low current units. And then the S748 and 772 are the high current units. The voltage range is from based on model number, but the range is 100 through 528 volt AC, and the high current units that we're working with today, their voltage range will be 230 to 480 volt. Electrical options include the standard dual channel STO. STO stands for safe torque off, and the inputs for the STOs are on the I/O connector, and they provide additional safety incorporated in the drive for the application for the machine. We'll cover that later in a WebEx later on. We have 3 expansion slots on the S700 product. Slot number 1 and slot number 2 are an overlapping location in the hardware, so you can't populate both slot number 1 and number 2 at the same time. It's either slot number 1 or it's slot number 2. And then we have a third expansion slot which does allow 1 additional card. So at any one given moment you could have 2 option cards in the S700 product. Plate screen we have in front of us is the S748 772 frame. It shows the ground plate located at the bottom. It ships in the container. It ships in the package with every product we sell. There is a grounding plate included. There are also horseshoe clamps that are used to secure the power cables on the grounding plate for strain relief and for EMI grounding. The importance of it is to prevent additional noise that would be coming in on the power connections, and the strain relief secures the cable in place for each application. Without that, you could stand a chance of the weight of the cable pulling free from the power terminal strip. Okay. One thing I could add here is the screens that we are looking at from this PowerPoint presentation are from the hardware manual, so at any point you need additional information, you can go into the hardware manual and look up these details. Okay, moving on. backplate mounting, also from the manual. We're giving you the dimensions for the clearance and separation of the amplifiers if you have them in the same cabinet. We give you the bottom dimension that gives you airflow, and the top as well. So the necessary mounting dimensions are shown. This is a side view of mounting the drive into a cabinet. Backplane should be unpainted and conductive, and you should have clearance, as it is calling out here, for 11.22 inches between the back of the cabinet door and the back mounting plate where the drive is secured. Okay, EMI shielding. The EMI shielding is for the incoming small signal leads for the I/O. The drive shows a protrusion off of one side that has slots located down the front of it, and the intent here is to put the shielded cable into place that is going to the I/O connectors. You remove the poly jacket from the end of the connector, exposing the braided shield for the cable, and then using a nylon stay tie, you thread it through one of the openings that is located up and down this plate, and you bring the grounded shield into the conductive chassis, grounding the I/O cable. And this works very well. Down below we show a horseshoe clamp that is in place. It is used for both the grounding plate, and there is also a small protrusion on the bottom for a horseshoe clamp for additional connections for smaller signal leads. Okay, so this is our EMI shielding methods for the front of the drive. All right, drive connector locations. I'll walk around this and explain quickly where the power and I/O and feedback connections are brought into the drive. Upper left-hand corner, we've got a power terminal strip for the incoming AC mains. XO is the connector, and line 1 through line 3 with the PE. The next connector located on top is the serial communications cable connection. It is for commissioning the product with the software that we provide, that Kollmorgen provides. X6 is its connection location, and it will also it performs RS-232 ASCII communications as well as CAN open communications coming into X6. Okay. On the face of the drive, you have two Ethernet connectors. The Ethernet connectors are used only in the event that EtherCAT bus communications is being used with the product. It's the only purpose for these two connectors. All right, below that we have a feedback connector. It's a 9-pin D X2, and that's the resolver connector for the feedback that might be located in the motor. The next connector down is X1. It's 15-pin D, and it is for the encoder input feedback from the motor. We have various feedbacks that come in on X1, from sine encoder to a commutating encoder or a pulse encoder, and lots of different styles of sine encoders, and the manual will cover that in detail. We'll show a few examples of it here later on. All right, the next connector down, X3B and X3A. This is the digital inputs and analog inputs, as well as the digital outputs. We'll go over those in detail briefly. The X4 connector is the 24-volt logic power input furnished by the customer for the drive. It also has the STO connections, dual STOs that are used, as we said earlier, in the safety circuit. Okay, the X9B connector is for the brake input power, and we have the customer must supply an additional power supply for the X9B if the brake output is to be used from the drive. And so X9B is the power in, 24 volts in to operate the brake. The drive manages the functionality of the power out to the motor brake, and that comes out on pins X9A. Okay. Then to the left we have the main power terminal strip, and the power terminal strip incorporates the connections for the regen resistor, minus RB and plus RB, as well as the motor phases, UVW. We also have the DC output, DC link we refer to it as, coming on this connector. And then the PE is positive earth, or protective earth. Okay, let's go to the next slide. In more detail, up on top we have the mains connection, XO. The three-phase power into the drive is not phase sensitive. Any of the three phases can be connected to any of the three connections. Okay. On the mains supply connections, we have a simple diagram here showing a contactor being picked up, bringing in the power. The fusing for this is the fusing that is required for this mains power in can be found in the hardware manual. What is the word for technical description? What is that page for the specifications? Technical specifications, that's what they call it.
Specifications.
Yeah. Okay, take two. Mains supply connection is shown in this diagram. It's simply a connector is being made to deliver the power into the fusing for the three-phase into the drive. This is XO. The fusing is covered in the technical description section of the manual. We tell you exactly which fuses are to be used, style and current rating. Okay. For the S748 and 772 drives, if you're operating in the power range of 208 to 240 volt three-phase, from these diagrams here for the supply coming in, it clearly is shown that we can accommodate different types of transformers as well as where the grounds are located. And again, this is only for the 208 to 240 volt. You have a delta shown here on the lower left with the ground actually out on the leg, one of the legs of the phase. That's acceptable. We still require a protective earth to be brought in directly to the same connection on the terminal strip. In the upper left here we have a Y connector with no ground, but the PE again is a requirement to be brought in. To the right we show a Y connection with a grounded leg for L1. That's an acceptable configuration. And then a delta which is showing a center tap ground. I'm sorry, not a center tap, but a center ground between the two phases. This is an acceptable connection. So everything here is acceptable. The grounds are optional or non-existent. And this is for 208 to 240 volt three-phase power. Now let's look at the high current, because things change a bit when you go to the, not high current, high voltage. This is just painful. I hate to hear myself talk in the first place, to myself. It's hard to stay on track. It's hard to keep. I'm trying to think back to what I did this morning, which is a wreck, because there's no way. Because I'm halfway through this and I remember just what I forgot to say on the last screen. And I'm like, oh, I didn't say anything about that. There's got to be a better way. It's like section, just do this one, stop.
We can do that.
Section, just do this one, stop.
We can do that.
Maybe better, because this is like I said, this just seems to, I can't keep my own continuity going. Okay, this screen is going to cover the low voltage of the S700 772, 208 to 480 volt inputs. We can accommodate multiple arrangements for the ground, and the transformer types can be Y or delta. In the upper left hand corner we show an example of a Y transformer feeding power into the drives, the 748 772, with no ground. We still require that the PE connection be made for the ground from the application. To the right we have an example of the Y transformer with a leg that is actually grounded, a grounded leg. This is acceptable for the low voltage, and again we have the PE ground connected. The lower left we show a similar but a delta transformer with a leg grounded, and again the PE connection is made to the ground. 208 to 240 volt is the key here. We have one more unusual method that we're showing, is 208 to 240 volt with a center or a grounded in the middle of an L1, L2, a center ground, and that is acceptable to the drive for low voltage. So we're very versatile on the low voltage version of this drive with grounds. But when we go to the high voltage version of this portion of the slide, the three-phase, we have a warning, and the warning clearly states an isolation transformer is required for 400 to 480 volt networks that are asymmetrically grounded or not grounded. So we're going to need transformers to give us the power. If we look at the perfect example here, is anywhere from 208 to 240 volt, a center ground Y is the best transformer and the best method for supplying balanced power to the drive. Other options: for 400 to 480 volt with no ground, a transformer is required. The primary is an ungrounded Y. The output of the secondary here is a Y with ground. That is what's required to keep the power and voltage balanced within the drive. And again, you can see that a grounded leg is acceptable on the primary, but the transformer creates the same scenario, a center tap ground of the Y for the power to the drive. Delta, the same scenario. So for 400 to 480 volt, there's a condition within the drive that will not allow you to have an unbalanced line. Therefore, you need a transformer and balanced power bringing the voltage into the drive. Okay. For the main power terminal strip on the bottom of the drive, motor power X8, we have the UVW connections are made. At the same time, you can see the regen resistor connections, the minus RB, plus RB. And the DC link is also on the strip, plus DC, minus DC. And protective earth. Okay, here we have an example for the motor power cable. The cable has a capacitance between phases and shield, and this specification is called out for in the technical description in the manual. We tell you exactly what the capacitance needs to be. And there is a cross-cut section here showing you the 4 conductors internal, one of them being for ground, the other 3 for the UVW phase. We have an internal shield, and then there's a poly jacket showing on the outside of it, but there is an overall shield for this cable style. Okay, for the motor power cable, if you are in an application that uses up to 25 meters of cable length, you can make the connections direct from the motor to the drive. No additional hardware required. For applications greater than 25 meters of cable length, we're showing a motor choke that's in series with the phases of the motor and the output from the drive, UVW. And the 3L is a partial of the model number that we provide motor chokes to sell into these type applications from Cole Morgan. And that information can be found in the hardware manual as well as their sales literature. The regen and braking resistor, showing the wiring from the power terminal strip X8, plus RB, minus RB. Fusing is called out for, and the regen resistor is an external regen resistor here. The specifications for the fusing is called out for in the hardware manual, as well as the resistance value for the regen resistor. Each amplifier of the S700 amplifier does not always use the same regen resistor, so you have to check the hardware manual and find out based on the model number of the drive what the regen resistor value is and what the potential wattage is for that regen resistor. Okay, from the X8 power connector, also DC bus link. The output for the DC bus link, we also refer to this as bus sharing. Minus DC between the drives, plus DC between the drives. And the benefit of the DC bus link is you can have additional capacitance to help filter and clean the DC power when all of the drives are tied together on a common rail, as well as sharing the regen power. The regen sizing and fusing would be based on all of the 3 amplifiers within the application and how much regen is expected to be taking place. But there is a benefit for the DC link and these simple features here. Okay. Moving on to the lower power, the X4 connection is for It's customer supplied plus 24 volt power supply. In this drawing we're showing a three-phase 24 volt supply being brought into the X4 connector, and they have dual connections for each so that you can daisy chain the 24 volt logic supply from one amplifier to the next, and the sizing of the power supply will depend on the number of amplifiers that are being connected. The current specifications are stated in the hardware manual for the 24 volt of each amplifier. Okay, if a holding brake is used in the motor, as we covered a little bit earlier, the 24 volt power supply must be furnished for the holding brake, and X9B is where that power is brought into, and then the drive has an output for the motor brake X9A. The feedback type. This screen covers the feedback type and primary feedbacks, resolver and sign encoder. The connections are X2 for the resolver and X1 for the encoders and all the different options on the encoders. We'll go over a couple of the details on these, on two of these types. For the resolver, we have from the motor side and the resolver mount, we supply out the reference voltage for the resolver, R1 and R2. This is out of the drive into the resolver. It's the excitation voltage. And then the S1, S3, and also S4, S2 are the cosine complements that are providing the information for the rotor shaft position back to the drive. The 15-pin D for X1 of the amplifier, that's where the encoder connections are made. And we have here the example being an NDAT sine encoder 2.2. We have a data channel and a data not. We have clock not. Then we have the voltage that is supplied from the amplifier to the encoder. And there are sense lines that can be jumpered in order to regulate the power more precisely for the encoder. In this situation, it would be about 5.05 volts. STO from X4 connector. The STO is safe torque off. Safe torque off 1 and 2 are provided in the drive so that the safety level of the application can be met. The STO stands for safe torque off, and simply if the inputs are driven with a plus 24 volt, if it's supplied on STO1 and 24 volts supplied to STO2, the drive is fully functional and can deliver power to the motor. But in the event that some external safety is compromised, the voltage is removed from either the STO1 or STO2, and the drive has the circuit that will prevent the transistors from functioning. That eliminates the possibility of the power out to the motor. This is covered in more detail in the hardware manual. We have simple descriptions and a detailed description, and there are wiring external is shown in the hardware manual, covering it in a lot more detail. X3A and X3B, digital inputs. They are active high inputs. They're driven by plus 24 volts. We have an enable input. It's devoted solely to enable. All the other inputs are programmable, 1 through 4. Input number 21 and 22 shown here are unique. They are either a programmable digital input or they are programmable digital outputs. So if you reference pin 6 and pin 7 of this connector, on the next screens or the following screens will show that there are outputs as well as inputs. Okay. For the input, hardware enable, it's active high only. It has PLC compatibility for IEC 61131-2 type 1. The DC ground floating reference ground. The digital ground must be connected and established for the reference. We are logic high when 15 to 30 volts is applied at 2 to 15 millivolts. And we go logic low state from -3 to 5 volts at less than 1 milliamp. The update rate of the enable circuit is 250 microseconds. For digital input 1 and 2, these are our high-speed inputs. They're active high only, 24 volts. Carries the same PLC compatibility, digital ground required, same voltages for high state, low state. But the update rate of these two inputs are 2 microseconds. So therefore the more critical functions within the drive application-wise for high-speed reaction to some event. 2 microsecond update rate. Digital inputs 3 and 4. They are P-stop and N-stop by default. P-stop stands for positive travel limit. N-stop stands for negative travel limit. The same apply for these inputs, active high only, same voltage ranges, and you'll see that the update rate of this input is 250 microseconds. Okay. Digital inputs 21 and 22. Again, they're all fully programmable. Same thing applies for the voltage and the currents. The update rate 250 microseconds. If you need outputs, digital input 21 and 22 can also be programmed for a digital output, digital out 1 and 2. If you note pins 6 and 7 from the previous screens, we are now showing it here as outputs. So the function of the outputs are merely just in software and setup. We have power supplied at X3 24 volt I/O and X3B digital ground. Carry the same PLC compatibility. The maximum output current's 100 milliamps and the update rate's 250 microseconds.